NMR spectroscopy was first applied in organic chemistry for the proton nucleus. This makes sense because organic compounds are covered by a skin of hydrogen atoms. The proton has high natural abundance and high sensitivity relative to many other nuclei. Today, the most common spectra are based on proton NMR, carbon-13 NMR, since carbons form the skeleton of organic compounds. Unfortunately, the magnetically active isotope carbon-13 with a spin of 1/2 has a low natural abundance, only slightly more than 1%. The remaining 99% is carbon-12, which has a nuclear spin of 0. Other nuclei that are commonly explored include other spin 1/2 nuclei such as fluorine-19 and phosphorus-31. This is due to fluorine's importance in pharmaceutically active compounds and phosphorus in many biomolecules. Proteins can be analyzed by NMR spectroscopy, although the ideal nucleus for this also has spin 1/2, which is nitrogen-15. Unfortunately, nitrogen-15 has very low natural abundance. So proteins that are studied by NMR are generally expressed in a nitrogen-15-rich environment. Other nuclei that are studied at Emory include boron-11. For a long list of other magnetically active nuclei, please see Appendix A in Chapter 6, which is on page 320. In the Emory Chemistry Department, we currently have 5 NMR spectrometers for solution phase spectroscopy. These include 2 instruments with 9.4 Tesla magnets operating at a proton resonance frequency of 400 megahertz, and for carbon-13, this corresponds to 100 megahertz. We also have an ancient spectrometer with an 11.7 Tesla magnet, which operates at 500 megahertz proton frequency. Our department has recently submitted a proposal to get a modern state-of-the-art 500 megahertz NMR spectrometer. We also have 2 spectrometers with 14.1 Tesla magnets. One of these is a relatively new Bruker instrument operating at 600 megahertz for proton resonance frequency. And we also have another 14.1 Tesla NMR spectrometer, which we acquired in 1999, and it is still running. The textbook provides a bit more detail on the phenomenon of nuclear magnetic resonance. I will skim over a few topics primarily because of their importance in acquiring the best possible spectrum. Figure 3.3 shows a single nucleus that is spinning with a vector in the same direction as the applied magnetic field of the NMR magnet. Since there is more than one nucleus in a sample, in fact, close to Avogadro's number, there are a large number of vectors, but there are very slightly more vectors in the same direction of the magnetic field over a slightly lower number of vectors in the opposite direction of the magnetic field. And so the net magnetization is in the same direction as the magnetic field. For a sample in the magnetic field, the NMR experiment then begins by delivering a high-energy, very short duration radio frequency pulse. This causes the net vector of the spins to tip by a certain angle. Typically, these days, this is set to 25 to 45 degrees, but for some experiments, and definitely in the past, the ideal tip was on the order of 90 degrees. Signal acquisition occurs at this stage. Then, the nuclei slowly relax so that the equilibria of spin distribution is restored with a slight excess in the same direction as the magnetic field. Here is the NMR experiment in a little bit more detail. The radio frequency pulse is very short. 8 microseconds tends to tip to 90 degrees, whereas a shorter duration, say 3 microseconds, causes the vector to tip by less, in the region of 25 to 45 degrees. With the 25-degree tip, the signal is not as strong, but it also does not take as long for the signal to relax to equilibrium. The acquisition time for the free induction decay signal, or the FID, is on the order of 1 second or slightly less. What is critically important is a recycle delay, and this allows for nuclear spin relaxation. If the spins are not allowed to relax before the next pulse is applied, then the signal acquired in part B will be weaker if only a few nuclei are tipped from 0 to 25 or 45 degrees. T1 is on the order of a fraction of a second to several seconds for proton, and for carbon-13, this can be on the order of a minute. T1 relaxation is enhanced by other nearby proton nuclei, and this is a manifestation of a through-bond nuclear-nuclear Overhauser effect, so that the proton spin relaxation occurs more rapidly with methyl groups or methylene groups. But a carbon with a single proton attached to it relies on a multiple bond relaxation effect, which is a slower process, has a longer T1. It's not unusual for alkene and aromatic CH to have T1 times on the order of 4, 5, 6 seconds. And the ideal to get the most accurate integration is to set your recycle delay up to 5 times T1. Now there's an obvious disadvantage to this, because if one is gathering a large number of scans, even a typical number of 16 acquisitions, for example, this delay time can really add up, and it decreases the number of samples that can be run per hour, per day. Therefore, the instrument manager has to strike a balance for the duration of the radio frequency pulse, with implications for signal intensity related to the degree of tip, along with the recycle time in order to get the best integrations. There's a second aspect to relaxation, which is T2, spin-spin relaxation, And for protons, this relaxation occurs on the same time frame as T1. Paramagnetic compounds, even paramagnetic impurities, will make T2 much faster. This gives a short free induction decay and broad peaks. So ideally, we want conditions where T2 is as long as T1 so that we get a longer free induction decay signal, which gives sharper peaks. The primary data that actually comes in an NMR experiment is the FID signal, the free induction decay signal. And way back when I was learning to use NMR spectroscopy, we would actually look at the FID to evaluate its quality, its symmetry, and its length for the settings of the instrument and the quality of the sample. A Fourier transform is required in order to convert the FID, or a collection of FIDs, into the familiar frequency domain spectrum, with frequency on the horizontal axis and intensity of the signal on the vertical axis. One of the most important aspects of nuclear magnetic resonance spectroscopy is that not all protons resonate at exactly the same frequency. And electron density will shield the nuclei, and that will slightly diminish the effective resonance frequency. So typically, for an instrument that is delivering radio frequency of 600 megahertz, 600 million hertz, shielding may decrease the frequency by up to a few thousand hertz. Absence of electron density may de-shield so that the frequency is slightly higher than 600 million hertz. And the range is on the order for proton of about 900 hertz. And this is what we typically will call parts per million. The standard that has been accepted for organic compounds is tetramethylsilane, which is highly shielded. By convention, other frequencies are reported relative to tetramethylsilane at 0 parts per million. Most proton frequencies in organic chemistry will extend from 0 part per million to about 10 part per million. Occasionally, highly shielded protons, especially those attached to electropositive metals, may be to the right of 0 part per million, and highly de-shielded protons, such as carboxylic acids or extensively hydrogen-bonded amides, may be to the left of 10 parts per million. The same thing applies for carbon-13 spectroscopy, and for the 14.1 Tesla that delivers 600 megahertz for proton, for carbon-13 the radio frequency is 151 megahertz. The chemical shift range for carbons is somewhat larger, which corresponds to 200 to 220 parts per million.